2.3 Continuity Part 2. Your objectives for this lesson are still to identify continuous functions, but also to determine whether or not a composite function is continuous and to apply the intermediate value theorem. Okay, so a function is continuous on an interval if and only if it is continuous at every point on the interval. So no exceptions, must be continuous at every point on the interval. A continuous function is continuous at every point in the domain. So this is the key phrase here, in the domain, which does not necessarily mean every point on the interval. Example 1, this is to clarify that a little bit. The reciprocal function y equals 1 over x is a continuous function because it is continuous at every point of its domain. So every point of its domain. However, it has a point of discontinuity at x equals 0. You can see that here. You could not draw this graph without lifting your pencil at x equals 0. And the reason it has that point of discontinuity is because the function isn't defined there. If you try to evaluate for x equals 0, you have 1 divided by 0, and as we have been over many times now, you cannot do that. Do not divide by 0. So this is an example of a function that is a continuous function, but it is not continuous on every point along the interval. Let's say this is -5 to 5. Okay. You might be asking yourself at this point, which functions are continuous? And my answer to that is many functions are continuous. So polynomial functions are continuous if, polynomial functions are continuous at every real number c because the limit as x approaches c of f of x equals f of c. So basically you can plug that in and you're going to get a value back. Rational functions are continuous at every point of their domains. So the last function we looked at in example 1 is an example of a rational function that is continuous in every point of its domain. They have points of discontinuity at the zeros of their denominators. Again, in that last example, you see the 0 of this denominator would be x equals 0, and it is discontinuous at that point. So that's because you can't divide by 0. Y equals the absolute value of x is continuous at every real number. So remember, this is your V-shaped graph. You can definitely draw that without picking up your pencil. What else? Okay. Exponential, logarithmic, trig, and radical functions are all continuous at points in the domain. So in their domains. There we go. Okay. Properties of continuous functions. If f and g are continuous at x equals c, then the following are also continuous at x equals c. The sums, so you could add those two functions together and that result will be a continuous function. Their differences, you could subtract f minus g, g minus f, you're going to get a continuous function. Their products, you can multiply the continuous functions, get a new continuous function. Constant multiples, so k is a real number, any number, and if you multiply k times f or k times g, you will get another continuous function. And last, quotients, so f divided by g will be a continuous function so long as when you're evaluating g of c you don't have 0. Same with g divided by f. F of c cannot be 0. Why? Because you cannot divide by 0. Okay, so what this comes down to is all composites of continuous functions are continuous. So examples of that we have y equals sine of x squared. So this would be y equals x squared, y equals sine x, and we have one of these getting plugged in to the other. This is a composite function. Since x squared is continuous and sine x is continuous, sine of x squared is continuous. The absolute value of cosine x. So remember, you have absolute value of x, and then we have cosine x. This got plugged in here. We have a composite function. Each of these is continuous, so we have a continuous composite function. So these are continuous at every point at which they are defined. Of course, if there is a point at which the functions are not defined, then the composite functions aren't going to be continuous there. Okay, this is a theorem. I do not have a specific name for it. Your book calls it Theorem 6 or 7, Theorem 7, and it's not known by the rest of the world as Theorem 7, but it is a theorem. So if f is continuous at c and g is continuous at f of c, then the composite g of f is continuous at c. So this is what we just went over. If you have two continuous functions, you can take their composite function and it will also be continuous. Okay, so example 2, show that y equals the absolute value of x times sine x all over x squared plus 2 is continuous. So let's look at the graph of this first. Pull this calculator up. Okay. So we have y equals absolute value of, the top is x times sine x divided by x squared plus 2. Okay. Let's zoom in, way in. So I'm going to make this negative 2 for the y's. That's a little better. Negative 1, 1. Okay. So I can see here, it looks like I could definitely draw that without picking up my pencil. There aren't any jumps tracing along here. No holes, no jumps. What happens if I go to negative 2? Not negative 2. Anyway. Yeah, so that looks like a continuous function. That looks pretty good. But let's look at this a different way, so not by graphing. So let's say g of x is equal to the absolute value of x, so that's this outside function. And f of x is equal to x times sine x over x squared plus 2. Okay, so I know then that this is a continuous function, so this is definitely continuous. We already established that. And this is a polynomial function. So this will be continuous as long as, well, at all points where this does not equal 0. Okay, so therefore, by the theorems in this section, since y is the composite of g of f, and we know that the absolute value of x is continuous, and f is continuous by properties of continuous and composite functions. Okay, so basically the theorems that we've looked at so far say that this is continuous. Since this is a composite, the whole thing is continuous. Okay. Last up, we have the intermediate value theorem for continuous functions. This is another big one, so you'll see this in the future. A function y equals f of x that is continuous on a closed interval a comma b takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c in a comma b. So this is your visual here, and you're saying you have this function, interval x values between a and b, and their y values are f of a and f of b. So you just plug those in. So somewhere on that interval, there is a number between them, and its y value is between their y values. It seems pretty common sense, but it has a nice name here that you should know, intermediate value theorem. So, intermediate value theorem. Know it, love it. Example 3. Is any real number exactly one less than its cube? So we're going to use the intermediate value theorem for this example. So this would be, if there's a real number, we're going to call it x. We want to know, will this ever equal its cube, x cubed, minus 1? Okay? We can rewrite this like this. So we're just moving the x to the other side. So x cubed minus x minus 1 is equal to 0. So now you need to look for the 0 value of the continuous function. So if we have f of x is this. Okay. So let's look at the graph. We have x cubed minus x minus 1. Graphing it. Let's go to the standard window. Okay. So you can see here that somewhere between 1 and 2, you are crossing that x-axis right here. So that is your 0. Your 0 is somewhere between 1 and 2. So this equals 0 between 1 and 2, which means that, well, this is where f of x equals 0, which means that there is some point between 1 and 2 where this is equal to 0. So since, again, on this interval, we know that if I trace 1, we have 1, -1, and 2, 5. So (1, -1) and 2, 5. Okay, so there are x values, since it's a continuous function, there are x values between 1 and 2. And 0 is a y value between -1 and 5. Since this y value is between -1 and 5, there is a corresponding x value between 1 and 2 that goes with this. So the answer to this is yes, there is such a number, and we know this by the intermediate value theorem. And I think, yes, that is it for this lesson.